it working?
Yeah.
Okay, so this is chapter 3 in the book. We'll talk about refrigerant and refrigeration. We'll talk also about vapor dome. It's okay, you're gonna can hear me. It's okay. You can see. So we'll talk about the vapor dome and the concept of superheating and subcooling. So we'll try to go as far as possible to explain those terminology. There are a lot of terminology that I would like you to remember. So you don't. So these are the objectives. We'll talk about high, medium, or low temperature refrigeration. What is considered low, high, or medium. So probably this is considered low refrigeration because we're not moving a lot of heat. But probably for freezing food, that's medium. And for other applications, it can be very, very high refrigeration. We'll talk about a ton of refrigeration. What does it mean? And why do we use tons instead of BTUs for refrigeration? So when you size a house and you want to buy a mini split or you want to buy central air, you have to talk about tons. How many tons do you need? And we'll talk about the basic refrigeration cycle. We'll explain the relationship between the pressure and the boiling point of water and other liquids. And probably you know by now what happens at the boiling temperature when we decrease the pressure. It will decrease. If we put water in vacuum, it will boil around atmospheric, around the room temperature. So this relationship will carry on with other refrigerants. We'll talk about the function of an evaporator, of a cooling coil. So probably it's something you've seen all the time, evaporator and condenser. So what does the evaporator do and what does the condenser do? So the condenser is a hot or cold. Is it inside or outside?
Outside.
Outside. Why? Because it's rejecting heat. So if you want to think about the cooling system in your car, what would be the ideal equivalent to? The ideal is the condenser. It's rejecting heat to the outside. So the condenser is always outside. It's condensing the evaporate, which makes it compressing into liquid. We'll talk about that. We talk about the compressor that normally used in residential and light commercial buildings. There are majorly two types of compressors. Either the piston one that functions like a car motor or engine, and there's the spiral one that keeps turning and squeezing the volume of air until it's compressed. We'll talk about that. Huh? Yeah. It's kind of like, it looks like a corkscrew pump, but it goes in spiral and just condenses the air. They are quieter, they have a lot of advantages, they're more expensive, and sometimes they are hard to repair. We'll talk about the function of the condensing coil and state the purpose of the metering device. So today in the lab, we'll talk about the metering device and how do we measure the pressure for the hot line and the cool line and see if it's acceptable or not. And based on that, we can determine whether the unit needs to be recharged or it's okay. We'll talk about the four characteristics of condenser when choosing one for refrigeration system. Colors. So refrigeration are not to be mixed. They are pre-made, manufactured to be with certain specification. What happens if you mix them? It will change the property, right? So every one of them is designed to boil at some temperature and condense at another. So they designed to be at this properties. If you mix them, you have lowered their property and the unit might not function the way it's supposed to. And thereby, you're not also allowed to mix them in a container because those are to be recycled. You are not to, you're supposed to put all refrigerants in their containers. If it's a reclamation container, you should say reclamation container and be sent out. And they're all color coded to reduce the confusion. So it's really hard sometimes to use the numbers. Sometimes the numbers can be erased. So they are color coded to be easier to detect. And we'll go through all the colors. There's plenty of them. There's a big list in the book. And there are some common ones and some of them that are less common. How do we store refrigerant? Again, refrigerant is flammable. It's very, very toxic. You don't want it to leak. What happens if a refrigerant touches your skin?
Comment, maybe?
Yeah, you get a frostbite and it will cause blinding. If there's flame, it will ignite. So it's very dangerous, toxic material. So we have to handle it with a lot of care. We'll talk also about how to properly connect the hoses and how much you can look out almost nothing. Supply refrigeration cycle. So we'll talk about that not in too much details, but at least I want to give you the gist of it so you can understand what's happening to the cycle. But we're not going to go too deep into it. So we have few refrigerants here, and you'll see the difference in the refrigeration cycle with respect to the pressure. So some of them require more pressure and less pressure than the other, and that makes them more expensive and more efficient. For smaller units, because we have smaller compressor, we're trying to economize and have something smaller that will run with the least amount of energy. We would like to have a refrigerant that will boil faster at lower pressure, so we don't have to do a lot of work to compress that. For bigger units, probably we'll have something more durable, a bigger compressor that will be able to compress this refrigerant at a bigger rate. And that's why they started with ammonia, because ammonia was a lot of compression rate, and we need a good compressor for that. I'll show you some compressor we have in the lab for high pressure compression. So refrigeration. The whole thing started in the 1900s, and it started with refrigeration using sometimes steam, and it evolved into using ammonia. However, ammonia is very toxic, and it wasn't very efficient. That's in the 1900s. So refrigeration process temperature ranges. There are different temperature ranges. What does that mean? How much heat we would like to remove, and what is the capacity we can do, and based on what compression. And how safe can we compress this gas without igniting, without causing any problem. So that's also what dictates what we need to do for compression. So high temperature compression is air conditioning. It's for comfort. Medium temperature, fresh food preservation, and low temperature is frozen food. So high temperature is also called low refrigeration in a way. So you're still keeping things at relatively high temperature, which is 75. It's high temperature, so you need lower amount of refrigeration. Medium temperature, that's for fresh food and fridges. And low temperatures for frozen food preservation and some scientific application as well, where sometimes you have to use liquid nitrogen for cooling. Any questions so far? Okay. So we talked about the second law of thermodynamics. So we said the first law is basically energy cannot be destroyed nor created. That's the first law. Second law talks about the flow of heat. We said heat flows from what?
Hot to
From hot to
cold.
cold. We are trying to make it flow from cold to hot. And we do that by using the properties of refrigerant or liquids. By playing with the pressure and temperature, we can actually pump heat outside. So it's similar to pumping water uphill. So heat naturally flows from warmer substance to the cooler. Heat will flow naturally from 100 degrees house if the outside temperature is 80. Makes sense. So get that in that quiz. So even though it's only 20 degrees, it will still flow. Until when? Until equilibrium. Correct. So until we have 80 in both of them, or the average, then we're not having more flow. So mechanical refrigeration is needed. That's the work we're talking about. So we said heat move from hot to cold. And if we wanted to move from cold to hot, we have to put in some work, and that work is the mechanical refrigeration. So what is the work we put in an AC? It's electrical motor running and turning everything on. That's the motor doing all the work, which is the compression. It's compressing the air, not air actually, refrigerant. And in doing so, once you let that high compressed air out, it will cool off. So probably you've noticed that with air. If you have a tire, for example, and there's a lot of pressure, and you have a hole in it, or start letting all the shredder valve out, the air will flow, and if you touch the valve is pretty cold. So the release of pressure makes it cool. So this is the base of the fridges, and usually in a fridge, the colder air always falls down. Why?
Because it's heavier.
It's heavier, has more density, and it's the law of nature. It's heavy, it's going to go down, and it's the buoyancy. So mostly, again, Bill always says that. Look at the new fridges, all the work, all the compressor, all the wiring is in the which part? The top, near the freezer. The freezer doing all the work, and some cold air will leak into the fridge. Some will go to the crisper and different parts, but mostly need all the cooling power in the freezer. Some facts here. This is why we are trying to talk, kind of segue into why we call it terms of refrigeration. I don't think you need to know all this information, but at least it helps to do the conversion. So it takes 144 BTU to melt 1 pound of ice at 32 Fahrenheit. So remember the experiment we did? We calculated the pound of ice. It took us 3 minutes to melt it using 1200 watts. So 2,000 pounds of ice, which is 1 ton, 1 metric ton, will require 288,000 BTU to melt. So if we multiply that, we get the conversion. So if melting 1 ton of ice takes place in 1 day, 24 hours, we get 12,000 BTU. So 12,000 BTU is the metric ton for refrigeration. So if you buy a big block of ice, that's 1 ton, 1 kilogram, which is 2,000 pounds, and leave this for 1 day. If it melts in 1 day, then you have 1,200 BTUs. I don't think you need to remember that, but for conversion sake, you just remember this number, which is 12,000 BTUs. That's the conversion between BTU and tons of refrigeration. Here's the block of ice, and this is how much it takes to melt the ice completely. And probably the beginning of fridges, as we talked about in the first class, they started in China, where they used to go to the mountains and bring some ice and put it underground and keep their food for preservation. And the same thing started in Europe, and ships used to go to the Arctic and bring some chunks of ice and bring it over. And of course, the bigger piece of ice, the slower it will melt. So you know this, when they have those cocktail parties and they have big statue of ice, that statue takes at least 6 hours to melt. So the whole thing was, okay, once the statue is melted, the party's over. It takes longer than you think. Even during sunshine, it takes a lot. Small ice, crushed ice, melts faster. You know why? Huh? More air, what else? Smaller. But what is happening there? Same amount of ice, same weight. Crushed will melt faster than a big piece of ice.
He can move as a density, yeah.
No.
Okay, what else?
He can move through it better
That's good. Why?
because it's not
It's
all
not solid.
Not solid.
Which means what? More surface area. More surface area for the air to contact with the solid and melted. And remember that, because that's the basis for all heat transfer. Remember when we say heat transfer, and we say Q equals area times U times delta T. This is the thing, surface area. So the radiator depends on surface area. To have a better heat transfer. Baseboard have a lot of fins for more transfer. Your car radiator has more rolls, more copper, more fins in it. If you close some of those fins, you're losing surface area, you're losing heat transfer. This thing also works for a heat exchanger in a boiler. It depends on surface area. There's a lot of people getting really creative with surface area. How can we maximize the surface area and the flow of one fluid over the other? So more surface area. So heat is pumped in a cool box to a warm room. That's the refrigeration process. And again, we say pumping heat is similar to pumping water uphill. You have to put a lot of energy. If you want to pump your water to the 3rd floor, you have to run your water pump out. And it requires a lot of energy and effort. So for air conditioning, a heat pump from inside to outside, with the inside temperature 75 and the outside 95. And we're trying to decrease the temperature. We're pumping against gravity. So we're pumping out against laws of nature. Cooling the indoor temperature 40, and the condenser outdoor temperature 125. If you want to keep the inside 75, you're going to have a coil temperature 40. Why? By the time the air cools off, comes out of the coil, it becomes 75, it loses a lot of, it will gain a lot of heat. So you need to have a lot of temperature difference to get that. The condenser coil outdoors is going to be 125, and you'll feel the heat is hotter than the atmosphere. If the atmosphere is 95, you need something hotter. The to have some rejection. And we go back to the equation here. The bigger the delta T, the faster you will transfer. So we want bigger difference. Indoor heat travels through the indoor coil, and system heat flows from outdoor coil to the inside air. So what we're doing actually, it's a bigger system of whatever you have in your car. You're trying to project the heat out of the engine through the radiator, and you pump it. And sometimes, I don't know if you have one of those older cars, if the car is cold, the radiator is sitting doing nothing until the car gets really hot, then you hear the water pump. But actually, until this day, if you open your radiator and look at it, in the beginning nothing is moving. The engine is cold. Once the engine is hot, the thermostat will turn on the pump and you start circulating. Okay, we'll spend some time looking at this beautiful picture that can be a little bit intimidating, but this is the basis of heating and cooling. Let's look at it from stage one. So we have this is the coil, has the cold refrigerant in it, which is evaporated. We have a cooling coil at 40 degrees Fahrenheit, absorbs heat from the room at 75, and you run air through it, and the air is moving through suction using the fan. This fan here is sucking the air inside from the room. So if this is your AC, it's basically a window AC. See the wall? This is your window AC. And if you look through the window AC, you see the fan. So the fan actually just circulating the air from the room back through the cooling coil. That's what it's doing over there. So and remember the fins over here? You see the fins when you open your filter. So you see the fins. If you open the filter over there, you see the fins. And basically the fan is just circulating the heat exchange between the air and the coil. So what is the fluid here? There are two fluids working. One of them is the outside, which is the air, and the inside is the refrigerant. The refrigerant is circulating continuously through the fins over here, and there is circulating as well. So what is the temperature difference? So the room is 75, there's 20 degrees difference here. That's very good heat exchange. That's a good rate. And the fan, if you run the fan, if you ever notice that if you run the fan too high, the room might not cool as fast, because you're not giving the air enough time to exchange heat with the coil. It's going too fast. So you circulate the fan, the air through the fan with the right speed over the coils. And what happens to the air that have gained some heat now? Gains some heat, it goes back to the compressor, it gets compressed. Because what happens to them when they get compressed? They get hot. So this thing gets really hot. That's why they put it in red. And it's completely hot here at the pressure of 125 at least. And the temperature now is 95 with the air outside. But this should be higher than that. So 125. But this coil that is at 125 degrees and the outside is 95. So again, there's 20 degrees difference, right? That's why, because we want to ensure proper heat exchange. If, for example, the temperature here is 100, only 5 degrees, think we will get good heat exchange? No, it's going to be lousy. That will reflect in the performance here. So if your condenser here is blocked or dirty or is not losing enough heat, you're not projecting heat outside to come back the way it is. It comes back again. What happens here? It's very compressed, pressurizing, and angry and hot. That's the throttling valve. Metering device, what it does actually, it does whatever we do with the garden hose. Squeeze the flow and open suddenly, so it releases more, kind of like depressurize the fluid. So it's liquid here, but you're evaporating here, giving it like less flow and more surface area. It's kind of garden hose. You press on it, the water have a lot of pressure and it spreads out. Otherwise it was flowing slowly. As it spreads out, what happens? It loses heat. It's become cold, almost freezing, frosty. And that will be here and we change it again. So let's think about it. There's a window air conditioning unit, and this symbol simplifies all the cooling process. From that stemmed a lot of ideas, a lot of improvement. So now if you look at the split unit, this is over here. However, the condenser unit is all the way to the other room, as far as possible. Why do you think that is? What is the point of that?
Because you want to eject the heat somewhere.
That's true. And what else? What do we notice in this area?
It only allows for one.
Yeah, compressor is here. And that's the most noisiest part and the heaviest. It's very heavy, it's very noisy, and in order to, we don't want the noise of the compressor, we don't want all this mechanism near us. Because again, our goal is to provide good ambient temperature without a lot of noise and least intrusion. So remember that all these Cs, they hum all night, and sometimes when it engages, wakes you up. I don't know if you have those ACs, but yeah, this is our clock really high engages. So we want the compressor outside to vibrate in its own time, do what it does, and we run a long, long line all the way to the throttling valve. And if we have some area exposed after that, it's always insulated. So the cold part of the pipe is always insulated. This is how you differentiate. It's cold, that's insulation. The hot is where they keep it exposed because you want people to see it. Question?
So with the compressor, does that just keep like, does that make the flow of the
Yeah,
refrigerant?
yeah.
That's the purpose of it?
Keep the flow going, also add pressure.
Alright.
It compresses the, it comes here as, it comes all the way here as liquid, almost liquid with some vapor, mixture. I'll explain that in the cycle. It comes out as mixture here, it gets compressed, then leave again. Okay? Let me spend some time in that because I think it's really important. With something I like to call the vapor dome. So can somebody remind me what is entropy?
It's how much energy you have in substance.
It's how much of the, yeah.
Excellent. That's H, that's entropy. So we're gonna go here with pressure. So this, can you see? So this is what we call the vapor dome. And this is called the saturation line. This is the critical point. So this is a plot of the pressure and the amount of entropy in the fluid. Okay? So I want you to imagine that anything here is gas. And the other side of here is liquid. This is called the saturation temperature. What is the saturation temperature? It's the temperature where both gas and liquid exist together. And it's only in this dome at this temperature. So at some temperature you'll have both gas and liquid together. And they are giving, okay, what does that mean here? It's where we have something called the quality. It's kind of scale. If the quality of this mixture, so we have a mixture here. Get on the color. This is gas and liquid. As we increase the heat, what do you think will happen? Here, we still have mixture, but how much of that mixture is gas? If we're at this point.
And hardly none.
Huh?
No, most of it.
Most of it, which is mean 100%.
Mhm.
So we're gonna call this 100%. As we go down, this is all liquid. It's gonna be mostly liquid. And the quality will be a 0 or 0%. That's the quality called X. I don't want you to remember all these details. I just want you to just imagine what's happening here. So we're operating in this dome. I'm playing with temperature and pressure. Increase the pressure and we get temperature. And all refrigerant have these properties. So as we go this way, if we keep adding heat, we jump out of the dome. And we become, in this area, it's called what? Superheat. So this is a superheated. So, as the name implies, it's superheated. It has so much heat that it can handle. So for steam, the steam has so much power. For refrigerant, again, superheat, it can reject more heat. This is the superheat region. So what would that area be called here?
Subcool.
Subcool. So it's cold enough to become liquid, but it's cooler than it needs. For example, what is at what temperature the water is liquid? Anything between 32 and up to 12. So at some pressure, at sea pressure, 212 is low boiling. So 210 is saturation. We're gonna have both in a container. So if we keep cooling, it's going to be subcooled. So we're cooling it, however, it's still liquid. It did not transform to solid. So unfortunately, water turns into solid 0. But refrigerant do not. You can freeze them, but they go lower and lower until it becomes solid. So this is basically the entire idea of subcooling and heating. And we keep jumping from here, we go to subcooling, then we decrease the pressure, and we go back in the dome, in here, and go back to this side. This is what we're doing. We're increasing the pressure, decreasing the pressure, and this is how we're getting superheated and subcooling. And these are the 2 points. We have superheating in the condenser, and subcooling in the condenser, and superheated in the evaporator. So let me ask you something. If the quality is 0.7, how much gas and how much liquid? In this graph here. If one is
Mostly
completely gas.
more gas than liquid.
Yeah, so how much if it's 7?
So it's 3/4.
Yep, so 70%, 73%
So
gas.
it's probably more good.
20, yeah, more gas than liquid. So what you can remember is the quality is one when we have completely gas. So we heated the material to a point when it's completely gas. Any more heat and it's going to be what? Super heated. So and what we're doing, we're keeping the heat. We're not adding heat, we're adding pressure. So we are making it to become superheated by only adding pressure. Because pressure and temperature go together. And this is how we are manipulating this cycle. I don't want you to remember all of this, just like if you can visualize, because you'll see this shape a lot. For example, if you look at your book at page 66, it's the beginning of Freon. You see this dome shape? Yeah, see the dome shape? That actually has also pressure and enthalpy, and this is your vapor dome. It goes up and down, those lines are the saturation line. Again, I don't want to go too much into the science of it and the physics. At least you know the critical point, where we have both temperature and so as we go up, we still have mixture here, but at this point we have equal pressure and temperature, and they both have liquid and gas. So anything outside the dome? Superheated, cold, mixture, quality. That's all you need to know for now. If you have any questions, let me know. So over here, do we have subcooling or superheating?
And that is super easy, yeah.
Mixture of both.
Huh?
Mixture of both.
We have mixture, but what is the heat that's causing this to? We're adding heat to it, right?
Yes. So it's superheated,
It's superheated.
Yeah.
causing it to
Yeah.
cool.
Here it's going to be subcooled,
Okay.
rejecting heat. And it will come with time and practice. You don't need to know again all the physics behind it, but at least when you know this terminology, it will help you a little bit. Even for when you put the hoses on the AC, they are foolproof, so that you cannot mix them up. But it's also good to understand these terminologies. And we'll keep honing on it as we go along. Some facts. temperature and pressure relationship. All you need to know, as the pressure increase, temperature increase, the temperature decrease, pressure decrease. So water boils at 212, atmospheric pressure. What is atmospheric pressure? 29 mercury. What is vacuum? If this is atmospheric pressure,
Oh, Z, 14.
which is also 29.
Right.
So this is 14 psi, corresponding to inches of pressure of mercury.
14.
So if the pressure now is 29, you want to have vacuum, which is 0, I have to suck all this up. So it's going to be minus 29 pressure. Remember that I drew the column and it said all the way, one column, 1 inch square of air from here all the way to the end of the atmosphere. The weight of that is equal 30 inches of mercury. Water boils at 250, the pressure is reduced to 15 psi. So if the atmospheric pressure is 14.7, we added 3 psi, 3.3 psi, that's why we have 250. So the relationship is there. Do you understand that?
So 0.3 changes it that
psi.
much?
Yeah. Water boils at 40 degrees instead of 212. If the pressure is reduced to 0.02 mercury. So if we have absolute vacuum, we can, but actually now, since the room temperature is 70, we can boil water now with vacuum. And I will bring the vacuum funnel and I can show you how that is done. Very interesting. Okay, so just to think about it, if all liquids have this kind of properties and we can use pressure and we have compressors or we have pumps, we can use that to our advantage. However, it was not efficient because again, pumping and compressing gases at very high temperature is dangerous. So the rise of having refrigerants, which are a substance made in the lab that can boil very quickly and give off heat very quickly, made it easier to have small compressor this much that will lose cycle for us. And if you look at the new ACs, you can have a compressor as big as a Pepsi can. It's very small, it's doing the job. So they boil at low temperature, at low pressure, and temperature, and condense at high pressure and high temperature. Saturating temperature is the point at which in addition removal of heat will result in a change of state. That's the saturation temperature, which is here. So at saturation, you add any more heat, you'll do boiling and superheating. You take any more heat, comes up cold, and eventually it will what? Freeze. Freeze. So this is the saturation here. During change of state, the temperature remains constant. Why? Latent heat. Change of state. Intermediate temperature. As we change state from liquid to vapor, it's latent heat. Nothing will change. And we did the experiment with the ice, remember? As we melt the ice, the temperature was constant until we melted the entire ice. Then it remained constant throughout the boiling until we finished the entire amount of water. Okay, so in the cycle, these are the components. You want a break? 5 minutes break? Good? Good to break? Okay, we'll continue. So the evaporator absorbs heat from the area to be cooled. So the evaporator is what we have inside. And we said the condenser is outside. So the evaporator is evaporating the refrigerant. And that is sucking heat, as you can say, or like absorbing heat. And where is it absorbing the heat from? From the air circulating. So it's there being circulating inside, going out, and being cooled. And as we said before, there's no such thing as cool, it's just lack of heat. So it takes it out. The compressor can create the pressure difference that's needed to facilitate the refrigerant flow through the system. So as Spencer was saying, the compressor keeps the refrigerant going. It's called the pump, but and it's also adding pressure to the system. Condenser projects system's heat to the outside, and a metering device regulates the refrigerant flow to the evaporator. It's called the metering device, expansion valve, throttling valve, so many names. And if you do a heat pump, it's called a reversing valve, because it has the ability to reverse the cycle, and instead of evaporating, it will condense. Okay, so one by one, the evaporator is a heat exchange surface used to absorb heat. Located on the low pressure side of the system between the metering device and the compressor. Operates at temperature lower than a medium, being cold or conditioned. And absorbs heat by boiling at low temperature liquid into low temperature vapor. You don't have to remember all this terminology, as long as you know where is the evaporator, which is inside here, and what it's doing to actually, so remember how the throttling valve has small area, and suddenly it's open, so it's evaporating by reducing pressure. So we are reducing the pressure here, rubbing the pressure, so it will evaporate and eventually condense into liquid. And that will, so actually we're going from here, this area, and dropping the pressure. So it's going to absorb heat and become liquid. So refrigerant typically enters the evaporator at liquid vapor mixture, so 75% liquid and 25% vapor. So what is the quality? Can someone tell me? What the quality will be if it's 75% liquid and 25% vapor? Look at the chart.
Oh, it'll be liquid.
It'll be liquid, yeah.
But what is X? What is the quality?
Oh, it will just,
Maybe like 0.2, right?
It'd be like
0.25.
So if X always pertains to the vapor,
Oh, I got you,
Oh,
okay.
and then it'd be like
Yeah,
0.75?
huh?
0.75?
Since
no.
it's gonna be 0.25.
Right, yeah.
So we are as of quality, we're here. So X, the quality, if you ever hear, you're gonna hear that in power plant and here. X, the quality always talks about the vapor. So if this is 25% vapor, then X is
Right.
0.25. Superheat, it took me a while to understand that. It took me a while. It's not easy. So I appreciate the confusion. How is that? So superheat, the heat of a vapor above its saturation temperature. Okay. So it's saturation temperature. As we increase heat, what will happen? Go to above. Anything above this line, superheat. So also the evaporator ensures that no liquid refrigerant enters the compressor, which makes sense because the compressor that does not deal with liquid, it will break or malfunction. That's why we are going to have superheated vapor going into the compressor. No liquid should go in there. So when we go to that diagram coming from the evaporator, it's always going to be superheated. Where did the heat come from? Where did the heat come from to superheat the gas in the evaporator?
From the fan, I mean.
From where?
From
The room.
Inside,
From
yeah.
the room. Because how much temperature difference we have? 20.
20.
The room at 75, and this is at 55, then it's going to absorb some heat. Again, natural flow of heat. So the evaporator and superheat, again, more information. Equal to the evaporator outlet temperature minus the evaporator saturation temperature. Okay, this is very important, remember this. Design superheat is typically between 8 and 12 Fahrenheit degrees. And why is this important? When we go and put our hose for the manifold pressure, and we take the pressure, okay, and read in the manifold what is that temperature, pressure correspondence, and we measure the room temperature. If it's more than, if it's not between those numbers, something is wrong with the system. Either we have to recharge it, or it's malfunctioning, or something wrong with the compressor. So between 8 and 12, and we will do this in the lab today. When we look at it, we're going to make sure it's between 8 and 12. If it's 20, something is wrong. So we're doing design temperature for the superheat. So you put it in the, when you put your tube on the cold line, and you read the corresponding temperature on the dial itself, and you measure the room temperature or the line temperature, it should be between 8 and 12 pressure.
So with it between 8 and 12, does that say like the refrigerant's working properly and
Yeah.
everything? That's
It's being pressurized properly, the system is okay, it's not under shock. If you see a big difference, like 20 degrees or 40 degrees, something is wrong. So we have to go on charge system and check for leaks. Superheated vapor does not follow
Yeah.
a pressure temperature relationship. Why is that? What do you think of that?
Because
Weird, huh?
eventually it's gonna just,
Because it's already vapor.
It's only vapor. It's treated like gas. It's like air. Actually, we treat it as ideal gas, to be honest. So it's superheated. It's way over here, outside. Does not follow the pressure temperature relationship because it's completely gas. It's not liquid anymore. There's no boiling, and the particles are very far from each other. This is an evaporator. This is an evaporator over here. I can just show it to you. And you'll see this in the cooling, in the walk-in fridge. So this is for refrigeration, and probably they have, so from what you grasp right now, what would be the modification if you want to build a fridge, and to build an AC? What are you gonna modify? You're gonna have more compression, right? More compression ratio. You're gonna have different refrigerant, so it's not going to be the same, because you're doing more work. And probably if you notice in the refrigerator, we have a lot of insulation. We try to really not use a lot of heat because it's going to be really inefficient. Okay. More? Good. You guys are good? We'll brush over these things. We'll touch base on them again tomorrow. I mean, next week. And I think when we go and do it practically, it will stick more. So for a compressor, the pump, it pumps heat, light and vapor from the evaporator to the condenser by increasing the refrigerant pressure. So what we're doing right now, we have superheated gas coming all the way from the evaporator going to the compressor. The compressor, what we do, we just increase the pressure. The thing is already superheated, you're increasing the pressure to it, so it will be subcooled. We'll see why. So it will reduce the pressure on the low side of the system, so it goes all the way here, so it's really hot. But increasing the pressure, actually reduce the pressure here. On the low side of the system, and increase the pressure on the high side of the system. So superheated gas goes all the way through the cycle over here, and we decrease the pressure from the evaporator side because we are vacuuming stuff going into the compressor, and goes to the other line, very compressed liquid. They didn't go too much into what happened inside, but basically what happens is you have a lot of gas that's already been hot. It's already been hot, you adding pressure to it, make it into liquid, or compressed vapor, and it's going through the condenser to reject heat. So it's very, very hot, usually around like 225 degrees. So there are two types. There's the scroll one that was talking about, reciprocating and rotaries. The reciprocating one with a piston, so it will have small pistons going up and down. And this can be connected to a crankshaft. So they go up and down. It's like an engine. The ones I saw actually for the General Motors back in the days, they were like 4 cylinders. 4 small cylinders coming up and down. And they rotate just like an engine with a crankshaft. We have the reciprocating compressor, which actually will work like a syringe with two. There's a piston in it, goes up and down, and there's an outlet over here, and an outlet over here. So as it goes up, the pressure increases and goes out from a relief valve. As it goes down here, the pressure will decrease and this fluid comes over here. And the scroll one, it has, it works like a screw pump. So you have vanes. You have a big rotor over here with vanes. The vanes get like smaller and smaller as we go along. So they go through a groove. So you think about capturing some air, And you run this groove using centrifugal motion until it goes to a small and small and small groove, spiral groove until it increases its pressure. And it has the advantage of being very quiet and it's very concentric, so it does not vibrate as much. Okay, so it look like this is the scroll, this is the rotary one, has a compressor in it, suction part and ejection part. It just goes up and down and pumps something and eject it out. Oh, then have the reciprocator. That's weird. Okay. So the condenser again rejects the heat, sensible heat and latent heat from the system that was absorbed by the compressor and the evaporator. You find it in the high pressure side of the system, so the high pressure also have the high temperature. The refrigerant condenses from high temperature vapor to high temperature liquid. So it's called Latin compressor. So it compresses. So we had, let's imagine that superheated vapor came all the way from the evaporator. Came all the way completely vapor as the compressor. It was already hot. We added more pressure to it. So as we add more temperature, pressure to it became more heated. It rejects some heat and becomes liquid. When things lose heat, become liquefied. So instead of liquefied, become hot liquid. High temperature liquid. So you also can remember that the condenser condenses thing. If you condense gas, it will become liquid. That's one way to think about it. Even in an aerosol can, with spray paint, it's basically compressed liquid. You're putting a lot of pressure, and it comes out. So condenser temperature is determined by the high side of pressure of the system, and the refrigerant is subcooled at the output of the condenser. And subcooling again is going back to the beginning of the curve. We're cooling something that's already liquid, so it just has some heat that it wants to absorb some heat because it's lacking heat. So saturated air cooling systems are designed to operate at a minimum of 10 degrees of subcooling. Okay, we have about 3 numbers to remember now. Superheating, temperature was between 1 and what?
8 and 12.
8 and 12, and now we have the subcooling between 10 degrees. If you can remember those numbers, probably have.
Well, one more time, it was just minimum of 10?
Yeah,
Okay.
that's a minimum of 10. It could be more, but minimum of 10. Up to 12 it's okay, but don't want to be minimum of 10. So if you see something less than 10, you know something is wrong. Got a question?
Yeah, so if it goes up, like if it goes up to like 40 or something like that?
That's too much.
Yeah, like
Okay.
is there like a
Yeah,
maximum?
15 or 20, depending
15,
on the AC, and sometimes it will show on it.
Alright.
High efficiency condensers operate at more subcooling temperature, since for high efficiency condenser, so you can get more than that. I don't know how much, probably you should put it level on the machine.
So if your condenser is plugged up with pollen, would that mess with your,
Definitely. We'll see that. We'll have it running and we'll cover up the
Yeah, but
condenser.
it will only go for like 12.
It won't reject the heat and you'll see the pressure drop.
Yeah.
So, so it becomes very interesting. It's kind of like magic when you look at it. It's very good. So this is more explanation about the process of subcooling. So let's think about it. Again, they try to illustrate everything in the R22 window. R22 is done, right? And you notice the color is light green. So you have to know light green is no good. It's not the code anymore. They do have substitute for that will operate at the same temperature and pressure. Because we have a lot of good equipment that has been designed for this purpose and they don't want to be all at once. So let's look at it a little bit. We have suction line from the evaporator, right? And we said this temperature is really high, superheated, a completely vapor coming in. The pressure is 287, 278, temperature is 200. Go all the way to the condenser. As it goes around, see, not the temperature, it starts dropping temperature, because again, we're running air coming at 95. This is at 125, so we have 30 degrees temperature difference. So eventually it's gonna lose heat, lost some heat. And it's still pressurized. So we kept the pressure constant. Pressure was constant, but we lost some heat. So what happened?
Went back towards like this.
It's gonna be some cool.
Liquid, but it's high pressure.
Yeah. So we keep the pressure constant. You see, look at the gauges. Here, the gauge is 278, and it's supposed to be the same over here. There is a gauge that says the same thing. The pressure does not change, but the temperature is decreasing. So we went below the line here. So we went to subcooled completely, and so you're gonna get some cooled liquid to the expansion valve. What the expansion valve does, give it a lot of space and release the pressure. You release the pressure, which you go here, you're gonna get a lot of heat. What happened? What did I do?
It's perfect timing for you hitting the blackboard, too.
Almost over, you think?
So,
Yeah,
So-
it's 7:25.
I think that's good. We'll stop now. We'll recap next week. I'm continuing that. And again, this is the most important chapter of the entire book. If you know how this works, and we'll learn how to take measurement, everything is downhill from now. So it's just like using tools, more safety, and reading the charts in the book. We'll post the video on Blackboard, and we'll continue that next week.